sweetie patootie math angel. Welcome back. This is Decaf-Math ASMR. I hope that you are getting yourself nice and comfy and cozy. Maybe taking care of whatever you need to get in the mood for some relaxation, or just getting ready for bed. I just hope that this video gives us a moment for some peace and quiet, and there's nothing to worry about right here and right now. I will be checking a solution that we got in a previous video, the last one I think. So it's an answer that we got from a example of using the Laplace transform. Here's the actual question itself. It's an initial value problem, and in that video we used the Laplace transform to solve this, even though if we move the 2y over, we can get a Bernoulli equation. So there are other ways to solve this, but we use the Laplace transform, and I wanted to just check our actual answer to make sure that it's correct. So the checking process is more about just doing some calculus. It's a very basic derivative, but it is a separate skill in and of itself, and I wanted to take the time to do this separately so that, one, we can all experience the satisfaction of everything just working out. Check. And that's just universally satisfying no matter what level of math or life we're doing or at. But this is also going to be maybe some nice review for anyone who just wants some extra practice or to kind of quiz themselves too. No pressure or anything. So let's get comfy, and you can totally just zone out as well and let the math just unfold. But I'm going to make sure that this function is indeed the correct answer. So in order to do that, I did want to mention, since this did come up, that this is a unique solution. This is an initial value problem, so we are given these conditions. If we were not given these initial values, then we could just get a general solution. And the general solution, or a general solution, is basically just a class of possible solutions. It's a pattern, so we might get something like C1 e to the stuff plus C2 e to the stuff. It depends on our characteristic polynomial or equation, and it depends on like the actual equation we're looking at. But in this case, it's a second order differential equation, so you might hear these words like second order, homogeneous, real solutions, that kind of thing, and how many solutions you have. So whenever you see or hear the phrase general solution, you might have like this form like C1 e to the stuff plus C2 e to the stuff, or something like that. We're not going to get too into it, but it's basically a class of solutions where you can replace those constants. But in this case, because we're given these specific values, we were able to solve for C1 and C2 to get our specific solution. But that's the idea of a general solution there, okay? So this should be the unique function that satisfies this, and this. Okay, so what do we do here? Well, let's first make sure that these initial conditions hold. So this is a little bit of something for our algebra friends. If you watched through the last Laplace transform example where we actually got to this answer, there was a bit of algebra as well, right? We did some partial partial fraction decomposition, we solve for a and b, and so 2 equations, 2 variables. So we got a little bit of algebra in, and that's what we're going to do right here too. This y of 0 is 0 just means that we are going to try to check. So this is all checking. We are going to put in 0 in place of t. This is our whole idea of our input-output thing. In this case, it's just if I give you an input for t, this is the function, so this tells me what to do with that t to give you a corresponding output. So in this case, y of 0 is going to be putting in 0 wherever I see t and simplifying. So I have 2/3 e to the 2 times 0, and 2 times 0 is 0, so you have to do an order of operations, minus e to the negative 0, which is just 0. Doesn't even really make sense. 0 is not negative nor positive, so negative 0, it's just 0. And so here, e is our Euler constant, the 2.78, whatever. And so that constant to the power of 0 is 1. To the power of 0 is 1, unless we are talking about our ambiguous case of 0 to the 0. But e is not 0, so that's nothing to worry about here. So these are each 1. So 1 minus 1 is 0. So we have 2/3 times 0, which is indeed 0. And we're just following the order of operations here. Everything inside the parentheses first. So 1 minus 1 is 0. 2/3 of 0 is 0. So that is very good. And it doesn't hurt to give us some extra check marks when we need it, right? So that's our y of 0 is 0. Then when we want to check y prime of 0, so I can't just do this straight away. What I have to do is, this means to take the first derivative of y with respect to time, and then we put the 0 into that function. So I'll leave this kind of blank, but I do need to do y prime of t first. So just in case this is something that confuses you or has confused you in calc, this is not the same. Y prime of 0 is not the same as y of 0 prime, because necessarily depends on the function, but y of 0 is going to be a constant, and you might have learned that the derivative of a constant is 0, so this is going to be 0, but y prime of 0 means to take the derivative of y first to get that function, and then you put in 0 like we did here. So it's not like y prime of 0 is always 0, okay? So this doesn't contradict itself right now. So we have to take the derivative of this first. So let's take the derivative of 2/3 times e to the 2t minus e to the negative t. So we can keep that constant. It's up to you how you want to do this. If you want to distribute the 2/3, that's fine, but it is a property for the derivative to be able to just pull out a constant if it's multiplied in front, because the derivative is linear. It's linear, so because it's based on the limit. So you can take this as a linear transformation. You can pull out a constant, and you can also take the derivative of this thing and then minus the derivative of this thing. So it kind of looks like we're quote-unquote distributing it, but that is important if you're going to use that actual property to know where it comes from. So we are pulling out this 2/3. We're going to take the derivative of e to the 2t, and then minus and the derivative of e to the negative t. So when I take the derivative of e to the 2t, I actually need to do the chain rule, right? Because the derivative of e to the t with respect to t is e to the t. The nice thing about this exponential function is the derivative of it just stays the same. But here we have e to the stuff. It's e to the 2t, so it's not just e to the t. So if this were e to the t, I would expect the derivative to be e to the t. So I write down what I expect it to be, which is e to the 2t, but then I have to do the chain rule, meaning I have to multiply by the derivative of this stuff, and the derivative of 2t is 2. So I just plop that out in front. So e to the stuff, the derivative of that, and what I mean by stuff is just the outside function. The f of x is, or f of t is e to the t, but the inside function, this g of t, is 2t. So this is a direct application of our chain rule. We're going to do the same thing here. We have minus, but if it's e to the t, the derivative is e to the t, so e to the stuff, we'll just keep it the same, but because it's negative t and not just regular t, positive t, I have to multiply by the derivative of negative t, which is negative 1 in front, and negative of negative 1 is positive. So this is our y prime of t. So when I plug in 0 now here, that's what I'm going to do. To check y prime of 0 is I put in 0 wherever I see a t. So I have 2/3 2e to the 0 plus e to the 0. Okay, and this is just for the sake of writing it all out, but usually when you confirm, that is really nice for initial values with exponential functions, because e to the 0 just always goes away to 1. So this goes to 1, and that's just easier to work with. So we have 2 times 1 plus 1. So this is 1 as well. So e to the 0 is 1. So we have 2/3 times 2 times 1 is 2 plus 1. And that equals 2/3 times 3, which equals 2. So that is indeed, we got this part and this part. Okay, so that's great. So that is the nice part about initial values, is you're talking about t equals 0 usually, and that just makes it all really nice. Dealing with 1s and 0s are really nice. All that's left to check is that this function actually satisfies our actual equation. It's kind of the most important part, I think, but these initial values are important to make sure that we got the correct particular solution. But let's make sure that this actually works as well. So we already have y prime of t right here. So this part's taken care of. We'll just end up plugging this in. But then we need to take one more derivative one more time, right? So 1 y prime prime of t. So the derivative of y prime of t is y prime prime of t. The second derivative, again, you would expect e to the stuff that the derivative is e to the stuff. So you would think it's e to the 2t, but because 2t is not t, you have to multiply by the derivative of the stuff up on top. So that's another 2. And then same thing here, you would think it's plus e to the negative t, but chain rule again, you just put in negative because the derivative of negative t is negative 1. So plus negative is negative e to the negative t. So typically if you're working with the exponential function, the derivatives kind of go in this cyclical or recursive kind of pattern here. You're always multiplying by another 2 here, and the sign for this part changes from positive to negative to positive because that's all that you're doing, is doing this chain rule, right? So then we have y prime prime is 2/3 4e to the 2t minus e to the negative t. And I'll just leave it like that, but you can, again, distribute. If we end up needing to, I will, but this is our y prime prime, this is our y prime, and this is our original function. So we have all the pieces here to actually check this. So this, I think, is the ultimate ASMR, because if we are on the right track, everything here should cancel out to give us 0. That's kind of why I picked this particular example first, because I don't know what's more satisfying than everything just working out, you know what I mean? Like, let's just give us all the checks. Check. So we have y prime prime of t, which is 2/3 of 4e to the 2t minus e to the negative t minus, where are we? Minus y prime, so that's just this one. And then minus 2 times y, so that's minus 2 times this original function, and 2 times 2/3 is 4/3. So I'll just go ahead and do that. So remember that we are trying to check our answers. We're not just going to write this equals 0. We want to actually somehow simplify this to equal 0. And these are not like terms or anything like in parentheses, so you're going to have to distribute everything out. That's okay. So we're going to multiply through, and hopefully all of our pieces do cancel out when we group everything together. So let's do the algebra here. We have 8/3 e to the 2t minus 2/3 e to the negative t minus 4/3 e to the 2t minus 2/3 e to the negative t. Just have to trust the process. Minus 4/3 e to the 2t plus 4/3 e to the negative t. And do these cancel? Well, let's see here. If we look at our e to the 2t terms, we have 8/3 e to the 2t minus 4/3 e to the 2t minus another 4/3. So 8 minus 4 is 0. So these cancel. Nice. And then if we look at our e to the negative t terms, we have negative 2/3 minus another 2/3 plus 4/3. So those cancel. So indeed everything equals 0. Shoop, 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 shoop. How nice is that? Awesome. We had all the checks here. Good job. Good job, good job, good job, good job, good job. Nice. So we have this function here. It satisfies our 2 initial conditions. It satisfies original function. So this is our unique solution. And without this, we would just have a general solution of the form c1e to the 2t minus or plus c2e to the negative t. So we were able to get the 2/3 because of this. So I think we did it, which you probably know I already kind of at least mentally checked this before I posted the last video, because I wouldn't want to post an actual incorrect answer in our question, but I did a quick check. But it's really nice and satisfying to actually work it all out and actually check it to really make sure. So now we are a lot more confident in our solution, and we can do some more Laplace transform examples, or we can do more Bernoulli, or we can do other second order or whatever, separable functions, all of the above. Have some fun with it as well, but we'll just keep on jumping around. I hope that you enjoy that. I hope that you enjoy kind of covering whatever topic we feel like. If you want some more basic videos, let me know as well. I have several playlists going, and I'm happy to spend whatever quiet time together. So I will see you around for more math very, very soon. If you are asleep right now, I'm wishing you sweet, sweet mathy dreams. And if you're going to continue and I'll see you around for more math very, very soon, okay?